We often move through life as if time were a river, its currents flowing at a uniform, unyielding pace from a fixed source to an inevitable sea. The tick of the clock, the turning of the calendar page, the steady march of seconds into minutes, minutes into hours, these are the anchors of our daily existence, the assumed constants upon which we build our schedules, our memories, and our futures. This intuitive, almost visceral perception of time as an absolute, an immutable backdrop against which all events unfold, is deeply ingrained in our consciousness. It's the bedrock of our sanity, the framework that allows us to make sense of cause and effect, of past, present, and future. Yet, what if this comforting linearity, this unwavering tick-tock, is merely a simplified human interpretation of a far more intricate and fluid reality? What if the very fabric of time, the dimension we inhabit and are seemingly bound by, possesses a hidden elasticity, a capacity for variation that eludes our everyday senses? Imagine a universe where the river of time doesn't always flow at the same speed, where its currents can eddy, slow, or even briefly surge, influenced by forces we have yet to fully comprehend or acknowledge. This isn't the realm of science fiction fantasy, but rather a tantalizing whisper from the frontier of physics, a suggestion that our most fundamental understanding of temporal progression might be incomplete, perhaps even fundamentally flawed. This exploration will venture beyond the easily observable, delving into the forgotten, the esoteric, and the nascent scientific inquiries that propose a universe where time is not a rigid, unyielding master, but a dynamic, responsive participant. We will begin to peel back the layers of our conventional understanding, not to dismantle the practicalities of our temporal experience, but to reveal the astonishing possibility that the passage of time is not a universal constant, but a variable shaped by factors that could, in theory, be harnessed or at least understood. Prepare to question the very rhythm of existence as we embark on a journey into the science of temporal variation, a path that promises to redefine our relationship with the most elusive dimension of all. For centuries, humanity's grasp on time was as firm and unyielding as the bedrock of existence itself. Isaac Newton, the titan of classical physics, painted a universe where time flowed with an immutable, majestic regularity, a cosmic river unaffected by the currents of matter or motion. This was the era of the universal clock, a grand unseen mechanism ticking with perfect synchronicity for every observer, everywhere. Time, in this Newtonian framework, was an absolute, a silent, unchangeable constant against which all events were measured. It was the ultimate impartial judge, its passage indifferent to the grandest celestial waltz or the most intimate human whisper. This elegant simplicity, however, was built upon a foundation that, while robust for its time, ultimately proved to be a magnificent, yet incomplete, representation of reality. Even as the gears of Newtonian mechanics turned with such reassuring certainty, whispers of doubt began to stir in the hallowed halls of philosophy. Thinkers, wrestling with the subjective experience of duration, pondered whether this universal clock truly accounted for the entirety of temporal existence. Was time merely a passive backdrop, or did it possess an active, perhaps even malleable, quality? These early inquiries, though lacking the empirical tools to rigorously test their hypotheses, planted the seeds of a profound question: what if time wasn't a constant, but a canvas upon which the universe itself painted its ever-changing masterpiece? They mused on the elasticity of moments, the way joy seemed to make hours vanish and sorrow to stretch seconds into eternities, hinting at a depth to time that eluded the rigid equations of the era. The very success of classical mechanics, its unparalleled ability to predict the motion of planets and the fall of an apple, ironically also highlighted its blind spots. While it masterfully described the there's what of motion and the how of force, it remained curiously silent on the earth when in a way that truly delved into the subjective or the relative. The equations of motion, while powerful, treated time as a parameter, a fixed coordinate, rather than a dynamic participant. They offered no mechanism to explain the subtle, yet pervasive, ways in which our perception, and perhaps even the very fabric of reality, could influence the rate at which moments unfolded. The limitations of this classical understanding became increasingly apparent as scientists began to probe the universe at its extremes, the infinitesimally small and the unimaginably fast. The predictable tick-tock of the Newtonian clock, so reassuring in its constancy, began to falter when confronted with phenomena that defied its absolute decree, setting the stage for a revolution in our understanding of the universe's most fundamental dimension. The absolute, it seemed, was beginning to fray at the edges. The rigid, unwavering tick-tock of the Newtonian clock, so reassuring in its constancy, began to falter when confronted with phenomena that defied its absolute decree, setting the stage for a revolution in our understanding of the universe's most fundamental dimension. The absolute, it seemed, was beginning to fray at the edges. It was Albert Einstein, with his audacious special theory of relativity, who dared to propose a universe far stranger and more wondrous than previously imagined. His foundational postulates were deceptively simple, yet their implications were profound. The laws of physics are the same for all non-accelerating observers, and the speed of light in a vacuum is constant for all observers, regardless of their motion or the motion of the light source. This latter point, the unwavering speed of light, became the linchpin for a radical reimagining of time itself. Imagine two observers. One is stationary, perhaps enjoying a leisurely stroll. The other is traveling at a significant fraction of the speed of light. According to Einstein's revelations, time does not flow at the same rate for both. For the traveler, time itself would perceptibly slow down relative to the stationary observer. This is the phenomenon of time dilation. It's not that their clock is malfunctioning. Rather, the very fabric of spacetime is stretching and compressing, and time is a component of this fabric. The faster you move through space, the slower you move through time. This effect, though minuscule at everyday speeds, becomes dramatically pronounced as one approaches the speed of light. To grasp this concept, consider the famous twin paradox. Imagine twins Alice and Bob. Alice remains on Earth, while Bob embarks on a journey in a spaceship traveling at near light speed to a distant star and then returns. From Alice's perspective on Earth, Bob's clock ticks slower due to his high velocity. Therefore, when Bob returns, he will have aged less than Alice. Bob, from his own frame of reference, experiences time normally, but his journey through space effectively used up less of his temporal progression compared to Alice, who remained relatively stationary. The paradox lies in the apparent symmetry. Couldn't Bob argue that Alice aged less? The resolution lies in the acceleration. Bob's spaceship must accelerate to reach high speeds and decelerate to return, breaking the symmetry and making Alice's frame the inertial one for comparison. This thought experiment, far from being a mere intellectual curiosity, is a direct consequence of the continuum's elasticity, demonstrating that time is not an absolute, universal constant but a relative, malleable dimension intertwined with motion. Einstein's general relativity gifted us a profound shift in perspective, moving us beyond the simple, clockwork universe of Newton. It revealed spacetime not as a rigid stage upon which events unfold, but as a dynamic, interwoven fabric, susceptible to the very presence of mass and energy. Imagine this fabric as a vast, invisible sheet. When you place a heavy ball on it, it creates a dip, a curvature. Similarly, massive objects like stars and planets don't merely occupy space, they actively distort the spacetime around them, creating these gravitational wells. This distortion isn't confined to space, it profoundly impacts the flow of time itself. The intricate dance of mass and energy dictates the tempo of existence. Where the fabric of spacetime is more deeply curved, where gravity's pull is strongest, time itself slows down. This phenomenon, known as gravitational time dilation, is not a theoretical abstraction but a measurable reality. Atomic clocks placed at different altitudes, experiencing slightly different gravitational forces, have demonstrably ticked at subtly different rates. A clock at sea level, closer to the Earth's massive core, will run infinitesimally slower than an identical clock atop a mountain. Extend this concept to the colossal gravity of a black hole, and time, from the perspective of an outside observer, would appear to crawl to a near standstill. This means that the very force that holds galaxies together also acts as a cosmic conductor, orchestrating a symphony of temporal rhythms across the universe, a gentle hum that slows the passage of moments in the presence of overwhelming mass. The universe doesn't simply possess time, it actively shapes it, bending and stretching the seconds according to the gravitational weight of its constituents. This understanding dismantles the illusion of a universal, unyielding clock, replacing it with a fluid, responsive dimension, perpetually influenced by the grand, silent forces that govern the cosmos. The universe sings a slow, resonant lullaby to the passage of time. The universe, in its grand, silent theater, offers us tantalizing glimpses into the profound plasticity of time, far beyond the subtle shifts experienced on Earth. These are not mere theoretical musings but observations etched into the very fabric of reality, particularly in the crucible of extreme astrophysical environments. Imagine standing at the precipice of a black hole, a cosmic abyss where gravity's grip is absolute. Here, time, as we commonly perceive it, doesn't just slow down, it effectively grinds to a halt. Light, struggling to escape the crushing gravitational well, is stretched to such an extent that its frequency shifts dramatically, a phenomenon known as gravitational redshift. This redshift is our direct observational evidence. Clocks ticking near a black hole would appear to tick infinitesimally slowly to a distant observer. Similarly, the enigmatic realm of neutron stars, the incredibly dense remnants of collapsed massive stars, presents another stage for time's peculiar dance. Orbiting a neutron star, or even residing in its immediate vicinity, would subject one to gravitational forces so immense that time would unfurl at a noticeably different pace compared to regions with weaker gravity. The powerful magnetic fields and intense radiation emanating from these celestial bodies further contribute to the complex interplay of forces that warp spacetime. These observations are not just astronomical curiosities, they are fundamental to our understanding of the universe's most energetic phenomena. Consider the life cycles of massive stars. These stellar giants, destined for spectacular supernova explosions, are born, live, and die under the influence of gravity. The rate at which processes unfold within and around them, particularly in their final, dramatic stages, is inherently tied to the local gravitational field. For a star approaching its end, especially if it is part of a binary system where one component might be a black hole or a neutron star, the time dilation effects become significant. Material accreted from a companion star onto a compact object will behave differently depending on the gravitational potential it traverses. This means that events like the ignition of fusion in a stellar core, or the outward propagation of shockwaves leading to a supernova, can be subtly, yet measurably, influenced by the curvature of spacetime. The very duration of these cataclysmic events, as perceived by an observer far removed from the gravitational intensity, would be altered. Our understanding of stellar evolution, from the birth of stars to their fiery demise, is therefore incomplete without accounting for these profound temporal distortions. The universe, it seems, is not just a stage for cosmic events, but an active participant, shaping the very rhythm of existence. While the dramatic dances of black holes and the warp-speed journeys of hypothetical starships capture our imagination, the subtle art of time dilation is not confined to the extreme edges of the cosmos. It is a constant, pervasive phenomenon woven into the very fabric of our terrestrial existence. Even at the pedestrian speeds we traverse our planet, and within the relatively gentle gravitational embrace of Earth, time itself undergoes infinitesimally small, yet undeniably real, stretches and compressions. These are not grand, earth-shattering shifts, but rather the whisper, quiet hum of a universe perpetually in motion, constantly recalibrating its temporal rhythm. Consider the simple act of a person living at sea level versus someone residing atop a towering mountain. The individual at higher altitude, experiencing a slightly weaker gravitational pull, will, over the course of a lifetime, age a fraction of a second more than their sea-level counterpart. Similarly, the atomic clocks that define our precise measurements of time, when flown around the globe at high speeds, demonstrate measurable discrepancies compared to their stationary counterparts. These effects, though minuscule on a human timescale, are far from theoretical curiosities. They are the tangible proof that the continuum of time is not a rigid, unyielding ruler, but a pliable, responsive medium. This fundamental characteristic of spacetime becomes critically important when we venture into the realm of advanced technology. The global positioning system, a technology so integral to our daily lives that we often take it for granted, would be utterly useless without a profound understanding and meticulous correction for time dilation. The satellites orbiting Earth are moving at considerable speeds and are in a weaker gravitational field than we are on the surface. If the clocks on these satellites were not adjusted to account for both special and general relativistic time dilation. The positional data they transmit would rapidly become inaccurate. Within minutes, the errors would accumulate to kilometers, rendering navigation impossible. The fact that your smartphone can accurately guide you through city streets or pinpoint your location in a remote wilderness is a testament to humanity's ability to grasp and harness these subtle, yet powerful temporal distortions. It underscores that the forgotten science of slow time is in reality a cornerstone of our modern world, a quiet enabler of our interconnected lives. The universe, at its most fundamental level, is a bewildering dance of probabilities and interconnectedness. While Einstein's relativity elegantly describes how massive objects warp spacetime, leading to the gravitational time dilation we experience, the quantum realm whispers a different, more intricate story. Here, at the very fabric of existence, time's steady march can become surprisingly fluid, influenced by forces we are only beginning to comprehend. Imagine the universe not as a rigid clockwork, but as a vast, shimmering ocean, where the currents of quantum phenomena can subtly nudge and bend the very flow of time. We are increasingly exploring the profound intersection of relativity and quantum mechanics, two pillars of modern physics that, until recently, seemed to occupy separate universes. Yet, as we delve deeper, the connections become undeniable. How might the bizarre behaviors of particles at the quantum scale, such as superposition and quantum tunneling, interact with the temporal distortions predicted by relativity? Could the very act of observation, a cornerstone of quantum mechanics, somehow influence the rate at which time passes for a subatomic particle? These are not mere philosophical musings, but active areas of scientific inquiry, probing the very nature of reality. The concept of quantum entanglement, often described as spooky action at a distance, offers particularly tantalizing possibilities. When two particles become entangled, they remain linked, sharing the same fate no matter how far apart they are separated. If one particle's state is measured, the other instantaneously reflects that change. Now, consider the implications for time. Could entanglement, in some as yet unexplained way, create a form of temporal connection across vast distances, allowing information or influence to traverse spacetime in ways that defy our classical understanding? Could two entangled particles, separated by light years, experience a shared temporal anomaly, a subtle synchronicity in their passage through time? These speculative ideas, while still on the frontiers of theoretical physics, suggest that the forgotten science of slow time might be deeply interwoven with the quantum tapestry, hinting at a universe far more dynamic and interconnected than we ever imagined. The remote wilderness settlement, powered by the subtle manipulation of temporal distortions, is a testament to this nascent understanding, a quiet acknowledgement that the deepest secrets of time may lie not in grand cosmic structures, but in the infinitesimal, yet potent, realm of the quantum. Our journey into the forgotten science of slow time necessitates a profound exploration of the human mind, the intricate biological and psychological machinery that acts as our primary, albeit often unreliable, chronometer. It's a fascinating paradox. While the universe operates on predictable physical laws, our personal experience of time is a fluid, malleable construct, sculpted by the very currents of our consciousness. The subtle stretches and compressions we feel, the way moments can drag on endlessly or vanish in a blink, are not mere illusions but direct consequences of how our brains process information and navigate the world. At the heart of this subjective temporal distortion lie a complex interplay of psychological and neurological factors. Our attention, for instance, acts as a powerful lens, focusing our awareness and, in doing so, influencing how quickly or slowly time seems to pass. When we are deeply engrossed in an activity, our attention is fully engaged, and the passage of time often feels accelerated, a phenomenon known as flow. Conversely, moments of boredom or anticipation, where our attention is fractured or fixated on the future, can make time crawl at a glacial pace. Neurologically, this is linked to the release of neurotransmitters like dopamine, which plays a crucial role in reward and motivation. Higher dopamine levels, often associated with engaging activities, can lead to a perceived speeding up of time, while lower levels, characteristic of monotony, can result in a slowing. Our emotional landscape is another significant architect of our subjective temporal experience. Fear, for example, can trigger a heightened state of alert, flooding our system with adrenaline and causing us to perceive events as unfolding in slow motion. This survival mechanism, designed to provide us with more time to react to danger, effectively stretches out moments of intense emotion. Conversely, joy and happiness can have the opposite effect, often making time seem to fly by. Memory, too, plays a pivotal role. The way we encode and retrieve memories profoundly impacts our retrospective estimation of time. Vivid, emotionally charged memories, often stored with greater detail, can make past periods feel longer and more substantial, while periods filled with routine and less memorable events can seem compressed in retrospect. This is why vacations, filled with novel experiences and heightened emotions, often feel longer than a similar duration spent in routine. It is crucial to distinguish these internal, subjective experiences from the objective physical time dilation described by Einstein's theory of relativity. While physical time dilation occurs due to extreme speeds or gravitational fields, altering the fundamental fabric of spacetime, our psychological time dilation is an emergent property of our biological and cognitive processes. It is a testament to the brain's remarkable ability to create a coherent narrative of experience, even when the underlying temporal data is being dynamically reinterpreted. The remote wilderness settlement, powered by the subtle manipulation of temporal distortions, is a testament to this nascent understanding, a quiet acknowledgement that the deepest secrets of time may lie not in grand cosmic structures, but in the infinitesimal, yet potent, realm of the quantum, and the equally intricate architecture of the human mind. Understanding these internal chronometers is not just an academic pursuit. It is a key to unlocking a more profound appreciation for the nature of our own existence and our relationship with the temporal flow that governs it. The implications of comprehending time dilation extend far beyond the theoretical musings of physicists and philosophers. They ripple outward, touching the very fabric of our technological present and shaping the audacious possibilities of our future. Consider for a moment the pulsating heart of scientific discovery, the particle accelerator. Within these colossal machines, subatomic particles are propelled to velocities approaching the speed of light. Here, the relativistic effects of time dilation are not merely an abstract concept but a palpable, measurable reality. Without an intimate understanding and precise calculation of how time slows for these particles as they accelerate, the very experiments designed to probe the fundamental building blocks of the universe would yield nonsensical, uninterpretable data. The exquisite precision required in these endeavors, from tracking decay rates to analyzing collision outcomes, hinges entirely on our mastery of temporal mechanics. It is a testament to human ingenuity that we can not only predict, but also harness these subtle stretches of time for the advancement of knowledge. Looking ahead, the prospect of high-speed travel, a staple of science fiction that inches closer to tangible reality with each passing decade, presents an even more compelling case for our temporal understanding. Imagine journeys across vast interstellar distances, where the speeds involved necessitate a profound engagement with Einstein's theories. An astronaut embarking on a voyage at a significant fraction of light speed would experience time at a slower rate than those remaining on Earth. This temporal disparity, a direct consequence of time dilation, would lead to fascinating, albeit potentially disorienting outcomes. While the traveler might age only a few years, decades or even centuries could have passed on their home planet. Navigating these temporal consequences, ensuring synchronized communication, and understanding the differing lifespans encountered upon return are critical challenges that demand a deep, practical grasp of time dilation. It's not just about reaching a destination faster, it's about understanding the temporal price of that speed and learning to manage its intricate, often mind-bending consequences. This knowledge transforms us from passive observers of time's passage into active participants, capable of shaping our journey through its very currents. Our ingrained perception of a universal no shatters when confronted with the profound implications of time dilation. The very notion that two events, simultaneous from one observer's vantage point, might occur at different times for another, is a direct assault on our deeply held assumptions about causality. If event A happens before event B for one person, but event B occurs before for another, the linear chain of cause and effect, the bedrock of our understanding, begins to fray. This isn't merely a theoretical curiosity, it has profound consequences for how we conceptualize the universe and our place within it. The philosophical ramifications extend into the age-old debate of free will versus determinism. If the future, or even parallel presents, can be influenced or even predetermined by relativistic effects, does that diminish our agency? If an observer moving at near light speed experiences time at a vastly different rate, are their choices, their very existence in that dilated frame, predetermined by the initial conditions of their journey? Or does the very malleability of time, the fact that it is not a rigid, one-yielding river but a pliable medium, actually open up new avenues for genuine choice? Perhaps free will isn't about defying a fixed timeline, but about navigating the branching possibilities inherent in a universe where time itself is a variable. The observer who experiences a dilated present might not be bound by a singular, predetermined future, but rather by a landscape of potential futures, each shaped by their unique temporal journey. This perspective suggests that our consciousness, rather than being a passenger on a fixed cosmic train, is more akin to a navigator charting a course through a multidimensional temporal sea. Reflecting on the nature of reality when time is not absolute forces us to confront the limitations of our sensory experience. We are, by nature, beings bound to a relatively constant flow of time, and our language, our science, our very thoughts are steeped in this linearity. When we consider a universe where time can stretch and compress, where simultaneity is a local phenomenon rather than a universal constant, we are forced to question the fundamental realness of our everyday experience. Is the objective reality that of the dilated traveler, or the stationary observer? Or is reality itself a mosaic, a collection of equally valid, albeit temporally disparate, experiences? This challenges the very idea of a single objective truth about the universe. Instead, reality might be a spectrum of temporal perspectives, each valid within its own frame of reference. The universe, in this light, is not a stage set with fixed events, but an ever-shifting, temporally dynamic canvas, where the act of observation and the observer's motion through spacetime actively contributes to the unfolding of existence. The forgotten science of slow time is not about embracing chaos, but about understanding a deeper, more nuanced order, one where time is not a tyrant, but a partner in the grand cosmic dance. Our existence is intrinsically tethered to the rhythmic pulse of the universe, a symphony conducted by the unseen hands of our internal biological clocks. These circadian rhythms, like ancient sundials etched into our very cells, dictate the ebb and flow of our physiological processes, aligning us with the predictable turning of our planet. From the subtle shift in hormone release that heralds dawn to the deep, restorative slumber that ushers in night, our bodies are masterful chronometers, meticulously synchronized with the external temporal cues of light and darkness. This innate biological timing is not merely a passive reception of cosmic signals, it is an active participation in the grand ballad of life, ensuring that growth, repair, and rest occur at their optimal moments. Imagine, however, a disruption to this delicate synchronicity, a sudden plunge into temporal conditions far removed from the gentle 24-hour cycle. What happens when the familiar cadence of day and night is replaced by an accelerated or decelerated flow? The implications for life, as we understand it, are profound. Extreme temporal dilation, where time inches forward with agonizing slowness, could render metabolic processes impossibly sluggish, while extreme temporal compression, where seconds flash by in a blur, might lead to cellular disintegration, unable to keep pace with the frantic temporal acceleration. Life, in its current form, is a product of a specific temporal environment. Pushing the boundaries of this environment could lead to unprecedented evolutionary pressures, or perhaps the complete cessation of biological function. This understanding of our embeddedness within a temporal framework is crucial. It suggests that our perception and experience of time are not solely dictated by external clocks, but by the intricate internal machinery that has evolved to harmonize with the universe's grand temporal design. The forgotten science of slow time invites us to explore this deep connection, to appreciate how our biological rhythms are not just a consequence of time, but an active force shaping our very experience of it. It is a journey into the biological underpinnings of our temporal reality, a reminder that within each of us lies an ancient, sophisticated clockwork, forever listening to the subtle whispers of the cosmos. The notion that time itself might not be a steadfast, unwavering river, but rather a current that could ebb and flow, was met with a fascinating cocktail of awe and skepticism in its nascent stages. Early scientific discourse, while rigorously exploring the theoretical frameworks, often found itself grappling with how to articulate these mind-bending concepts to a wider audience. Imagine the bewilderment as physicists began to suggest that a traveler moving at incredible speeds might age differently than their stationary counterpart. This wasn't simply a matter of clocks ticking at different rates, it was a fundamental challenge to the very fabric of shared existence. Public reaction, filtered through the nascent media of the day, often veered towards the sensationalized or the dismissive. Headlines, if they existed, might have screamed of time travel gone mad, or simply ignored the implications, preferring to focus on more tangible, immediate scientific breakthroughs. The inherent difficulty lay in translating the elegant, albeit abstract, mathematics of relativity into relatable terms. How does one convey the curvature of space-time, the dilation of time as a function of velocity and gravity, without resorting to overly technical jargon or analogies that, while helpful, could also oversimplify or mislead? Many found the concepts counterintuitive, clashing with our deeply ingrained, everyday experience of a universally consistent temporal flow. This disconnect led to a marginalization of these ideas in popular consciousness. They were relegated to the realm of science fiction, the fantastical musings of imaginative minds, rather than being recognized as profound truths about the universe, waiting to be understood. The true revolutionaries, those who dared to propose that our clocks were not merely measuring a constant, but were instead sensitive instruments responding to the dynamic nature of reality, were often met with polite but firm resistance. Their groundbreaking insights, the seeds of a deeper understanding of our temporal existence, were like seeds sown on stony ground, waiting for the right conditions to germinate and truly blossom. The initial whispers of variable time were often drowned out by the louder, more familiar rhythms of a world that believed time to be a constant, an unyielding master, rather than a malleable force. This early struggle to communicate and comprehend the subtle, yet profound, implications of relativistic time laid the groundwork for a long and often challenging journey towards its eventual acceptance and integration into our scientific worldview. Our current scientific endeavors are pushing the very boundaries of what we understand about space-time, venturing into realms where time itself behaves in ways that challenge our everyday intuition. At the forefront of this exploration lies the intricate dance of quantum mechanics and general relativity. Physicists are meticulously examining the phenomenon of time dilation, not just as a consequence of extreme gravity or velocity, but also through the lens of quantum entanglement. Imagine two particles, separated by vast distances, yet intrinsically linked. When one particle is observed, its state instantaneously influences the other, a connection that seems to defy the conventional flow of time. This spooky action at a distance, as Einstein famously put it, hints at a deeper interconnectedness, where the very fabric of space-time might be woven from quantum threads, exhibiting properties we are only beginning to grasp. The quest for a unified theory of physics, often referred to as the theory of everything, is intrinsically tied to our understanding of time. For decades, physicists have grappled with the fundamental incompatibility between the smooth, continuous nature of space-time described by general relativity and the discrete, probabilistic world of quantum mechanics. A successful unification would likely revolutionize our perception of time, potentially revealing it not as a linear progression, but as a more complex, emergent property of a deeper, underlying reality. Some theoretical frameworks suggest that time might not be fundamental at all, but rather an illusion born from the collective behavior of more basic quantum entities. This perspective opens up breathtaking possibilities. If time is an emergent phenomenon, could it be manipulated? Could we, in principle, alter its perceived flow or even, as some speculative theories propose, create localized pockets where time behaves differently? The implications of these cutting-edge investigations are staggering. We are on the precipice of discovering phenomena that could redefine our technological capabilities and our philosophical understanding of existence. Consider the potential for advanced propulsion systems that harness the very curvature of spacetime, or communication methods that transcend the limitations of the speed of light by exploiting quantum entanglement. Perhaps we will uncover new forms of energy, or even discover ways to interact with the past or future, not in the realm of science fiction, but through the rigorous application of physics. The journey to unlock the forgotten science of slow time is not merely an academic pursuit, it is a profound exploration into the fundamental nature of reality, a quest to understand the very mechanism by which the universe unfolds and to perhaps, one day, influence its rhythm. The echoes of these discoveries are already reverberating in the quantum loom, hinting at new realities waiting to be knitted into existence. The revelation that time is not a rigid, unyielding river, but a malleable current, capable of stretching and compressing, has profound implications that continue to ripple through our understanding of existence. We've journeyed through the celestial clockwork, witnessing how gravity itself can warp the temporal fabric, making moments stretch into eternities for one observer while mere blinks for another. This isn't mere theoretical musing, it's the bedrock of technologies that already guide our global navigation and communication. The very satellites that whisper directions into our pockets operate on principles that account for the subtle, yet significant, divergences in time's passage. We stand at a precipice, invited to shed the anachronistic notion of a universal, absolute time that ticks uniformly for all beings, in all places, under all circumstances. This ingrained perspective, a relic of a simpler, Newtonian universe, now feels as quaint as believing the Earth is the fixed center of all celestial motion. Instead, we are challenged to embrace a more nuanced, dynamic reality where time is intrinsically linked to motion, gravity, and the very fabric of space-time. Imagine a universe where your personal journey through moments is as unique as your fingerprint, a personalized temporal experience woven from your specific trajectory through the cosmos. This shift in perspective is not just an intellectual exercise, it's a fundamental reorientation of our place within the grand cosmic dance. It urges us to perceive our lives not as segments on a shared timeline, but as individual threads in an infinitely complex tapestry, each with its own pace, its own subtle distortions. As we contemplate the vastness of this relative temporal landscape, a sense of wonder naturally envelops us. The mystery of time, far from being demystified, deepens with every discovery. We are reminded that even as we unravel its secrets, the fundamental nature of time remains an enigma, a profound canvas upon which the universe paints its unfolding story. The quantum loom, mentioned previously, continues its intricate work, knitting new realities from the probabilistic threads of existence, and at the heart of this creation lies the ever-elusive, ever-present mystery of time. It is a humbling and exhilarating realization, one that beckons us to continue our exploration, to listen to the whispers of the chronometers, and to perhaps, one day, understand the true rhythm of the universe.